last talk today. The talk by Kadim was cancelled, so... Okay, Google. So it's a pleasure to welcome Gugu, and he will talk on the denseness of finitude of things.
Thank you very much. So it's a great pleasure to talk in this conference, so celebrating the 60th birthday of Marcelo. So congratulations, Marcelo. It's a great honor to talk and to, by circumstance, to give the last talk of this conference. So I would like to thank all speakers by the fantastic talks of this workshop and all the people that came to participate in this workshop. So it's so I will talk on a subject related to a conjecture by Jacob Palli. So this is a joint work with Fernando Lenarduzzi, who is now in Unesp of Rio Preto, but he was a postdoc. Well, he did his PhD at IMPA. He was a postdoc at IMPA under the supervision of Jacob for some years. And with Jacob, who is there, so Jacob is also our co-author in this work. So thank you very much, Jacob, for coming. A great honor to. So I will talk on a subject related to a very famous conjecture by Jacob, which was mentioned before in this workshop. Is the famous global conjecture on finitude of attractors. So let's start with some comments on the beginning of the modern theory of dynamical systems. So the hyperbolic theory was done in the 60s by Steve Smay and many collaborators, and Jacob in particular, and many other collaborators. So Pilk, Schub, Robinson, etc. So everybody knows about this. And so hyperbolic systems are an open class of dynamical systems which exist in any manifold, and which we can describe quite well. So we have a hyperbolic diffeomorphism in a compact manifold. We know that there are finitely many basic sets, so transitive pieces, in particular finitely many attractors and repellers. However, we know that hyperbolic systems are not dense, are not typical. So there are open sets of diffeomorphisms which are not hyperbolic and which can have quite different dynamical behavior. So, for instance, in the 70s, in this famous series of papers, Newhouse exhibited examples, so open examples of surface diffeomorphism, say in situ topology or Higher, with persistent homoclinic tangencies, and under some extra hypothesis of dissipativity, he could exhibit open sets of diffeomorphisms where residually the diffeomorphisms have infinitely many sinks, so infinitely many coexisting periodic attractors. And then in 1999, Christian and Lorenzo exhibited the same kind of phenomena, so in dimension 3 or higher, in the C1 topology, so open sets in C1 topology, where residually the diffeomorphisms have infinitely many sinks. So after that, so there was an ancient dream of describing all dynamical systems, and some moments people thought that, say, hyperbolic systems could be typical, could be open and dense. Classically, this is, fortunately or unfortunately, this is false. But Jacob could recover an important part of this dream by making a global conjecture on the behavior of dynamical systems. And it's a very ambitious conjecture that not only describes a dense set of dynamics, but also describes in some sense the bifurcation of this dynamics and the behavior of nearby diffeomorphisms. So it starts, Jacob's conjecture works in many contexts, so for diffeomorphisms, for flows, or for endomorphisms, for instance. say in compact manifolds or in intervals in dimension 1. It's the situation that we understand better. So Paley's conjecture says that the first statement is that there is a dense set of dynamical systems, so in these contexts, that have only finitely many attractors in a broad sense. So transitive attractors, not necessarily periodic, whose union of basins has full measure, has total probability in the manifold. Moreover, the attractors of these diffeomorphisms in this dense set D support a physical measure, which is an SRB measure. And so he also tells something about bifurcations of these dynamics. So he considers small perturbations in generic k-parameter families of dynamics. And then, so this is true in dimension 1. So in general, so the statement of the original statements are a little bit weaker, but anyhow, he also assumes stochastic stability of attractors, and that for generic families of one-dimensional dynamics, in total probability in the parameter space, the attractors are either periodic sinks or carry an absolutely continuous invariant measure, while this is proven for unimodal maps, but still open in this generality for multimodal maps. But in general, the conjecture is widely open, and we'll concentrate in this statement, indeed, in the weaker version of this statement. And so we work in C1 topology, and we'll prove this theorem that is a partial result on the direction of the first statement, still very far from proving the first statement of the conjecture. That's still very difficult. So it says that it's a theorem on, so the nickname of Paley's conjecture is Paley's conjecture on finiteness of attractors. So he will prove a result on finiteness of sinks, not a finiteness of attractors in general. So we proved that for a C1 dense set of diffeomorphisms of compact manifolds, the corresponding diffeomorphism has only a finite number of sinks, of periodic attractors, periodic orbitals. So the arguments of the proof could be extended in the context of flows and endomorphisms. So also in dimension 1, this is also known by Shen, Van Strien, etc. The theorems that shows that the density of hyperbolicity in dimension 1. So, in arbitrary dimension. In arbitrary dimension. We'll see that C1 topology. So the statement is just about periodic sinks. So as you see, the idea is not that sophisticated. So we begin with a system with infinitely many sinks. So if we start with a system with only a finite number of sinks, then there's nothing to do. But if you have infinitely many sinks, so infinitely many periodic attractors, then we will perturb the system, but very near, so in a small neighborhood of the attractors. And so we start with a Kupka-Ismail system. Kupka-Ismail systems are typical, are dense, either in the context of endomorphisms or diffeomorphisms. But, well, the official statements for diffeomorphism, but anyhow. We start with a Kupka-Ismail system and look for periodic orbits. Some of the periodic orbits, perhaps infinitely many of them are attractors, are periodic attractors. They are all hyperbolic because we have a Kupka-Ismail system. And so suppose that we have infinitely many sinks. We are just concerned with periodic attractors, so infinitely many sinks. What we do is to perturb the system in a neighborhood of the sinks, in small neighborhoods of the sinks, and we replace the dynamics by something else, but something that is not a sink. In some sense, we'll create so infinitely many attractors in some sense close to the sink, at least in topological sense, but anyhow, so it's not. So in this sense, we are not close to prove the whole conjecture, so the main conjecture, but we just want to prove the statement, so the denseness of finitude of sinks, or even of things which are conjugated to periodic sinks, because something is conjugated to a periodic orbit is a periodic orbit, which can be non-hyperbolic, but this way also can destroy. So. Okay, so we'll consider small neighborhoods of the basing of attraction of the sinks, and exactly because they are attractors, so the dynamics is split. Once you have a sink, so you have a basing of attractor, the dynamics in the basing of attractor are converging to this periodic orbit, and the rest of the dynamics. I will not move the rest of the dynamics, so the rest of the dynamics will be the same thing. I will only do perturbations in this in these neighborhoods of the basing of attraction. So I'm not creating new dynamics outside the basing of attraction of the sinks, and I want to understand what happens in this basing of attraction. Of course, I don't want to create new sinks which I cannot control, and so I have to. Anyhow, but there's no loss of generality in assuming that in appropriate coordinate systems. So we can, since the situation is split, so for each sink we have its basing of attraction and the rest of the dynamics, and we are doing things in C1 topology, it's not difficult to see that we can do this essentially independently. For each sink we do a perturbation, and at the end, if we are happy. Of course, there are strong sinks, for instance, can have a contracting fixed point with an eigenvalue much smaller than one that you cannot destroy. So any small perturbation, you still will have this sink, the strong sink. So we have strong sinks and sinks which are not too strong. So the first thing is to show that except for finitely many sinks, the other sinks can be destroyed by a epsilon small perturbation. So if you fix a positive epsilon, you want to show that, well, there are finitely many sinks that you can't do anything, so they will remain. But for the other, you can do something. So, but we can assume that the dynamics in the neighborhood of such a sink is linear. So let's use Frank's lemma. And okay, we can also perturb a little bit the derivative and assume that the norms of the eigenvalues are different, except, of course, for complex eigenvalues that have pairs of conjugate complex eigenvalues that have the same norm. This is okay. But for different eigenvalues that are not conjugate, I will assume that the norms are different. Okay. And now there is this discussion on strong sinks and weak sinks in some sense. So we have a periodic orbit. We can consider a composition of some consecutive iterates of the dynamics. So we have a periodic orbit, say of period M like this. We choose a large integer R, which can be related to epsilon, say integer part of 1 over epsilon. And basically, we will divide the orbit in blocks, so iterates in blocks of R terms. So epsilon is a small constant. R is a large constant integer in some sense. So we have these blocks. For each block, we have period M. We have essentially M over R blocks of size R. And, well, for each block, we have the composition, the derivative of the composition. The dynamics close the orbit is even linear. And, well, I looked at the norm of this composition and consider the product of these norms. So I claim that if the product of those norms is exponentially small, in M or in M over R, makes no difference because R is constant. If it's exponentially small, then this is a strong sink. You cannot destroy the sink. But more than that, this sink will have a large basing of attraction. You have a ball of fixed radius, depending on epsilon, R, etc., and in the size of perturbation I'm allowed to do, of course, such that, well, if I do a small perturbation, then not only the sink will survive, but it will have large basing of attraction. It will have a lower estimate for the volume of the basing of attraction. So we can only have a finite number of those guys, right? We have a lower estimate on the basing of attractor. So this is not very difficult. This is just so elementary remark in some sense, just by continuity of derivatives. So C1 dynamics. And of course, what we want to do is to take the other sinks and destroy them in some sense, or replace the remaining sinks by something else. Okay. The best situation in some sense is when we have a sink such that the sink has an eigenvalue or a Lyapunov exponent, better saying, which is close to 1. So all the eigenvalues are smaller than 1 because they are sinks. But if the Lyapunov exponent, so the average eigenvalue, is close to 1, it's not difficult to destroy the sink because you just multiply by something like 1 plus epsilon along the orbit. Again, using Franck's lemma that in a very small ball, much smaller than epsilon, you can multiply by 1 plus epsilon close to the center and by 1 outside the small ball. And, well, you can create, you can make the largest eigenvalue be equal to 1 in norm. So either a real eigenvalue, which is 1 or minus 1, or a complex eigenvalue of modulus 1. And then, again, we are in C1. We can replace the dynamics. So that's in these directions, which can be one-dimensional or two-dimensional. The dynamics is essentially the identity in the real case, or a rotation in the complex case. But outside this is contracting in some sense. And when we glue, we have an average, so something between 1 and 1 plus epsilon, but will not create expansion or more complicated dynamics. And then we can perturb this rotation or things like that. So for instance, if situation is more beautiful in the complex case, so in the case where you have two eigenvalues, so the largest eigenvalues are complex conjugate. And then we can transform this sink in a source or a saddle whose largest eigenvalue is slightly larger than 1. But near them, we create a small invariant circle, say, with an irrational rotation by a small perturbation. We have like a source or a saddle here. And the rest of the dynamics is contracting because I'm just doing perturbation in a very small ball. So we replace the sink by an invariant circle with, say, with irrational rotation if we want. And this will be an attractor, but not a sink. In this real case, we can essentially create identity. So we have globally something like an attractor. So but we can essentially replace first by something like the identity here. But we can create a sequence of saddle nodes. Well, of course, we can create a weak attractor. Well, the identity is not a sink, too, so we can have this. But we can create a weak attractor, but this is conjugated to a sink. Or a countable sequence of saddle nodes with the same period corresponding to something like this. So where is diagonal? So we have think like this, a sequence of saddle nodes tending to something like this. So, this is not very deep, but again, this is not a sink. This is something else. So this is the idea. But this is not the whole proof, because there is a complicated case. This is a simple case where, well, the eigenvalues are smaller than 1, of course, because we have a sink, but we have an eigenvalue, not a norm, an eigenvalue which is close to 1. So a Lyapunov exponent, so an average eigenvalue in some sense. So this is not the general case, and there are complications. So this is what I just said. If the eigenvalues are complex conjugate, we may perturb the new dynamics to obtain a saddle or a source. close to an invariant small circle with an irrational rotation, as I mentioned. And if the eigenvalue is real, we can create a sequence of saddle nodes converging to a periodic point over the same period. This is what I just said. OK. But how we do in general? So this is not necessarily true in general that we have an eigenvalue. We could have very large norm and very small eigenvalues, and this is the worst case in some sense. But so given a sink of period m as before, so you will assume that if you do these blocks of size r, so the product of the norms is in average is close to 1. So product of the norms is not very small. It could be very large, it could be exponentially large. The eigenvalues are smaller than 1. So we have an easy lemma, linear algebra. Typically, when we compose linear transformations, the norms are not very far from being multiplied. So have very expanding, so for instance, linear transformation. The composition, so either we have very bad luck or the composition will be also expanding. And just take, so I'm estimating the norm of AB with a rotation in the middle. So just take a unit vector that attains the norm of B, so such that modulus of BV is the norm of B. And then you look to BV, to the direction of BV. Of course, it could be in the most contracted direction of A. But this is a very bad luck, because we have this singular value decomposition A. So the norm of A is the largest singular value. So there is a direction where the norm is attained. And you have a complement direction. Of course, you can have bad luck, and the image, so BV could be here in this hyperplane or very close to it. But you can rotate. You are allowed to do a rotation. So if you can do an epsilon rotation, the component in this direction of the largest eigenvalue you can make to be of the order of epsilon. And then the norm of the image would be product of norm times epsilon. So this is a very easy remark from linear algebra. So when we are composing this norm, so the norm of the composition could be close to the product of the norms. But again, I need to work with eigenvalues, not with norms, and how we convert a norm in an eigenvalue. So let me mention a general fact, which is not optimal, but just a result in this direction. That, well, we can compose, again, composing with a rotation. We have a transformation with very large norm. We can compose with a rotation which is close to the identity, say epsilon close to the identity, and get an eigenvalue which is not too far from the norm of A. So I have this estimate that's epsilon to 4n, where n is dimension, is fixed with the dimension of the manifold, epsilon to the power 4n times the norm. So if after the composition this norm is close to 1, so I had an estimate on product of norms, then I use the first lemma to convert product of norms in the norm of the composition. Because I multiply by epsilon in few places, so I will have a factor like epsilon to power, essentially epsilon m, and this is 1 minus the rho of 1 to power m. So this is sub-exponential if epsilon is small. And so if I do this trick of composing with, say, random rotations, and so epsilon rotation well chosen if you want, along these blocks of size r, which is r is essentially m multiplied by epsilon, sorry. Then at the end, the norm is not very small. Again, it could be exponentially large, but it's at least sub-exponentially small. So it's not very small, the norm after the composition. And then we use this lemma to convert norm in eigenvalue. So to have an eigenvalue which is not very small. So how this lemma works, we have two cases. So if all the singular values are close, the first singular value is the norm. If all the singular values are close in the sense that the ratio is at least epsilon 4, the fourth power, then all the singular values are comparable in some sense, and So the norm and the inverse of the norm or of the inverse are comparable, and everything is okay. So you can compare eigenvalues to the norm directly. If not, then there is a large gap. So we have two consecutive eigenvalues, singular values, which are very, very different. This discussion is invariant by homotopy, so we can assume that one eigenvalue is larger than epsilon to minus 2, and all the other smaller singular values are smaller than epsilon squared. So we have, say, lambda I larger than and lambda I plus 1 smaller than epsilon squared. So lambda 1, lambda 2 up to lambda I are very expanding. Lambda I plus 1 up to lambda n are very contracting. And then we just consider the composition of the space. And consider, say, a cone with fixed angles, 45 degrees, dimension 2, but in general. So fixed angle. Since these singular values are much larger than this cone will be sent to a very, so it will be compressed, it will be sent to a cone like this. Of course, we have rotation, so this cone can be in a wrong position close to a bend. But then we rotate this. If you can do an epsilon rotation, so the opening of this cone is at most epsilon squared, say. And then you do an epsilon rotation, you put in a reasonable position, and then we'll have a cone. So we can, 45 degrees is not good, so perhaps epsilon. But we can choose a cone, so it's not a difficult exercise, which is invariant, which is sent, and we have a minimum expansion of at least epsilon to some power. So this is not difficult to prove, but this is not very precise, And in the worst case, we will need a much more precise estimate on how we can improve our eigenvalues. And then I needed to learn some linear algebra. Sorry. But we have, the worst case by far is the case when the norm is very large. It's not close to 1. It's exponentially large. But the eigenvalues are exponentially small in average. So the Lyapunov exponents are exponentially small. Then this is dangerous when you do Frank's lemma. Why? Because you want to glue. So you know that the norm is very large. You have a small perturbation which large eigenvalues. You just need an eigenvalue close to 1. You can do a smaller perturbation. But anyhow, there is a small perturbation. So the eigenvalues here are smaller than 1. Indeed, exponentially smaller than 1 in the worst case. Here, the perturbed thing, I can have eigenvalue close to 1, but still smaller than 1. But in the middle, the kind of perturbation I described first was just multiplying by 1 plus epsilon, or perhaps by 1 plus t epsilon for some t between 0 and 1 when you compose things. Multiplying by real constants commutes with everything, so the situation is easy to control for this perturbation, even if we do this interpolation. But here, we are composing with rotation. And we interpolate this, so we have here A, and here A times identity plus epsilon, so plus x, where x is a small rotation. But in the middle, we will have something like A times identity plus t of r, which r is the radius, times x. And we are composing things like this. We don't know exactly where are the values of r. We need to control this. We don't want to create non-trivial dynamics here with perhaps new sinks, etc. So this is a problem, so we need to be concerned. And so what is the idea? The idea is to, well, here I don't really need an eigenvalue 1 directly. They can be still small, but sub-exponentially small in terms of Lyapunov exponents. And I want to control iterations of things in the middle such that I can guarantee that they are still small. This is what I need to guarantee contracting behavior at last. And then at the end, I do this trick of multiplying by 1 plus epsilon everything. I can keep a a sink in this process, so a periodic sink, but I want to replace the eigenvalues by eigenvalues which are in average close to 1. So I have some large eigenvalue in the sense that it's smaller than 1, but the Lyapunov exponent is not too far from it. It's larger than 1 minus epsilon, say. Right? So, but I still want a sink here, because the last perturbation will be this thing of multiplying by 1 plus epsilon and creating an eigenvalue 1, because multiplying by positive constants is okay, so everything commutes. So we need a theorem, which is a non-trivial theorem in, say, linear algebra, which is Kreis matrix theorem, which says it's about transient behavior of, so have a linear dynamical system. So f of x is a times x. A belongs to GLN, so it's a linear transformation of Rn, which all eigenvalues is smaller than 1. So it's a sink, it's a fixed point, attracting fixed point. But for some a, if we consider the first iterate, a could have a large norm. A will be the derivative of this composition. We have a periodic point with large period. We are doing all this turn and considering the composition. So the a is not bounded in any sense. So I need to control infinitely many things. You remember. So a can have exponentially large norm, etc., but can have eigenvalues smaller than 1. And if you consider norm of a to the j, so norm of a, norm of a squared, etc., it could grow for a relatively long time, the graph, before tending exponentially to 0. And the question is, what's the size? I want to do a very small perturbation just to create an eigenvalue close to 1. Lyapunov exponent close to 1. So what is the size of this small perturbation that I need to do? So if we are precise in this answer, so we have a very small perturbation that creates an eigenvalue close to 1, but smaller than 1 in average, so the real eigenvalue is much smaller than 1, indeed, because we have this m iterates and m is large. So the Lyapunov exponent is close to 1, but the eigenvalue is still much smaller than 1. Then we can control the behavior of these compositions. These are perturbations of the m iterates. So you compose many times. At last, you tend to the eigenvalue. So the long time behavior has to do with eigenvalues. But there is this transient time. And exactly, so the size of this small perturbation is related to maximum for all j, because this tends to 0, but for some values of j it could be very large, to the inverse of this maximum. So we are considering perturbations which have eigenvalues larger than 1 in norm. You have this pseudo-spectrum. There is a nice characterization of pseudo-spectrum, which is written here, the first useful fact. Lambda belongs to the epsilon pseudo-spectrum if and only if there is an epsilon perturbation of A such that lambda is an eigenvalue of this perturbation. But it's, so the first definition was this, so the set of lambda, such that A minus lambda I has a very, so the inverse has a very large norm, has norm larger than 1 over epsilon. So this is the epsilon spectrum. Ka, in some sense, measure this, the size of the perturbation that you need to do to create an eigenvalue larger than 1. Because in this definition, rho epsilon of A should be larger than 1 in our case. So the question is, what is the minimum epsilon such that the perturbation is larger than 1 in some sense? It's related to this. And so, but the precise definition is this. And this is essentially a trivial estimate from but this is non-trivial. Indeed, there was about 10 or 12 intermediate results before reaching this this bound, so that there is a relatively large history of this problem. This was a conjecture of Kreis conjecture for a long time and was proven, well, not very recently, but say about, I would say 15 years ago or something like this. Anyhow, this is optimal. This is these bonds are sharp. There are some examples. And this is a constant. N is the dimension. E is E, 2 times 7. Okay, so this is constant. So this is very close to K of A. K of A is essentially this supreme, this maximum of the norm of A to the J. So this is Kreis matrix theorem, non-trivial thing, and we use this. So essentially it implies that we can make a perturbation of more or less of this order and create an eigenvalue larger than 1. And in the worst case, if we compose things like this, so essentially A plus T1x, A plus T2x, a very large number of unbounded Tn. N is very, very large, so that we are approaching the eigenvalue in some sense. So when we do this, so most of the time the Ti will be 0 or 1, but we don't know. In the middle there's something we cannot control. But here, if we develop everything, we will have 2 to the n terms. And this is sub-exponential, because A is already a derivative of a large iterate. M is the period, which tends to infinity in our case of Q. So we have 2 to the n's, but it corresponds to an mn iterate. So this is 1 plus little o of 1 to power mn. So the number of terms in this composition is not very important, so it's sub-exponential. And the maximum thing you can create, will be product of essentially Ti, A to I, or A to I minus 1, X. We have products of things like this. So if Ti is smaller than this, then this times this, the norm of this, will be always small. It will be always smaller than 1. And X is the size of 1. So all of these terms will be small, even if you have no control on the Ti's. So this will be sub-exponentially large, if it's large. And then you can multiply by 1 minus epsilon to allow power to be smaller than 1. So you have a perturbation where, at the end, you have an eigenvalue which is, so a Lyapunov exponent which is close to 1, we say 1 minus epsilon squared or something like this. And in the dynamics is contracting, you still have a sink. And then you use this trick, you multiply again by 1 plus epsilon, 1 plus 2 epsilon. No, so average between this and 1, and etc. And this is easy to control. So this is what is written there. So in the dangerous case, we compose with a diffeomorphism very close to the identity, so delta close, where delta is the inverse of this supremum of normal A to the J. And then, okay, this allows to control the dynamics in the gluing ring, so in this region where you are doing the gluing, and show that the dynamic, that we still have a sink. And these two facts are useful. So, of course, this characterization of epsilon, so the perturber spectrum, and these estimates. So these estimates on the norm of A minus lambda I minus 1. So because this implies that indeed the size of the perturbation, because we don't, in this definition here, we need to control the size of epsilon. So epsilon should not be very large or very, so I want epsilon of the correct size. On the other hand, we want to understand how far from 1 these eigenvalues lambda can be. And these eigenvalues after the perturbation are not much larger than 1. Are at most, say, E times n to the square or something like this, because of this relatively tight estimate. So if lambda is not, so it's sub-exponential, so it's at most constant, a constant depending on the dimension, then everything is okay. Indeed, the perturbation of this size can create eigenvalues close to 1, and but smaller than 1, and still the behavior in the gluing region is still contractive, so we still have a sink. And then at the end, we do this multiplication by 1 plus epsilon, by this averaging between 1 plus epsilon and 1, and conclude the proof. So there are some references. There's this book by Embry and Trefton, which is where so it's a non-trivial book, more than 600 pages, on the behavior of non-normal matrix and operators, etc., which in particular has a chapter on this Christ-metric matrix theorem. The main reference I use for this. So classical papers by Newhouse, Bonatti-Diaz, and Dimensions. So the other references you probably know better than me. So this is the original Paley's conjecture. And yeah, there's another paper on this conjecture, etc. So thank you very much for
Many thanks. Any questions?
If you already know that it's larger than 1.
Everything is invariant by homotopy. So indeed, I use this to create an eigenvalue smaller than 1, but close to 1 in average.
Okay.
But if it's larger than 1, but not much larger, I just multiply by 1 plus epsilon to the period and create a smaller. Indeed, in the end, I need to create smaller than 1 to guarantee that the dynamics in the green region is still contracting. And then I create eigenvalue 1 by this first trick of multiplying by 1 plus epsilon here and 1 here, because this is much easier to control, because I'm multiplying by constant multiples of the same matrix, and everything commutes. And it's easy.
If you are in a region of the Newhouse phenomena, that you have the stable manifold and unstable, and you have the two cantor intersect that you favor picture, and you do this, and you know already you have infinitely many things that it was produced, were created by this of the two cantor set, and you do your technique. What happened with those stable?
Well, in dimension 2, if we start on the diffeomorphism, so dissipative, then you need to create, so you have so the area is much smaller than 1, so you need to have an eigenvalue which is much smaller than 1, and an eigenvalue close to 1, so you need to do this to create these infinitely many saddle nodes. So infinitely many saddle nodes, or infinitely many, so you don't need really saddle nodes, but you need to create infinitely many things converging to, infinitely many saddle nodes, well, otherwise you would create an attractor. So, but, the question is, so if you have a strong contraction and an eigenvalue close to 1, perhaps it gives some information on, so you have a normally hyperbolic invariant curve in some sense with a strong contraction. Perhaps, so if we could bound from below the area, we could try to create, so perhaps after a perturbation, we could create a contradiction with the existence of infinitely many sinks with some extra hypothesis. So perhaps this gives an idea of something. So corresponding to this case where the sink is very strong in this sense, where you have a lower bound for the area of the Basinger attraction. Here you should have a strong normally hyperbolic curve. I don't know whether under some additional hypothesis we could bound from below the area. If this is true, we could prove in many other contexts that you only have infinitely many things. Of course, you have examples of infinitely many things. So you need some extra hypothesis that I don't know what it should be, but perhaps it gives some idea for something. I don't know.
Okay.
So in your procedure, once you start with example with infinitely many things, and you do all your perturbations, in the end you have finitely many attractors, so still infinitely many attractors.
Yeah, I still have infinitely many attractors because I have this. I didn't change the basing of attraction. I have this basing of attraction. They are going inside, and instead of having a sink, I'm creating something else. But for instance, here, in the case of this invariant circle with the rational, this invariant circle will be a kind of attractor. So they have this basing of attractor, things are tending to this invariant circle in some sense. So I'm cheating, of course. I'm creating, I'm still keeping infinitely many kind of attractors, but not sinks. Because I provided infinitely many sinks. And this is what
yeah, so this in particular gives a different, maybe different proof of the finiteness of sinks for the structurally stable systems. So where is hidden this please argument? In Kreis statement or?
Well, this is, as you mentioned, this gives a proof, so I can perturb and have only finitely many things. But I don't know. You need to compare the two proofs. But perhaps certainly there are similar ideas. So here there is a kind of price argument because I need to. So this is like a gas station problem. So this is a matter Olympiad problem that you have a road, a circular road with many gas stations, and the sum of the volume of the gas in the stations is sufficient to do a turn. The problem is to prove that you can start in some of the gas stations in order to be able to do the complete turn, and like price lemma. So you need to, in order to have this argument, you need to start somewhere where for all intermediate iterates, the norm is exponentially small, so the basing is you can bound from below. So you need an argument like this, which looks like price lemma in some sense. Huh? No, of course. At the end, I have as many attractors as before in some sense. So I'm cheating in this sense, but I only have finitely many sinks. But attractors, no, I still have all this basing of attractors. You need to have something inside. So yeah, in this sense.
Do you feel that now that you have those intervals as attractors, can you go the next step?
Yeah, so at some point I thought that perhaps I could do this with two eigenvalues and create circles. But in the example you mentioned, dimension 2, you have nothing to do. You just have 2 dimensions. You have one strong dimension and the other is close to 1. So in the dissipative case, so the area is exponentially contracting. So if you have an eigenvalue close to 1, the other one should be exponentially contracting. So you cannot escape from this one-dimensional case where you create infinite dimension. But perhaps with extra hypothesis, we could bound from below the size of this normally hyperbolic neighborhood because you have a strong contraction and a central manifold in some sense with eigenvalue close to 1. So perhaps this gives some information, but I'm not. So perhaps we can discuss later. I don't know. Perhaps it makes no sense what I'm telling, but it looked to me similar to this case where we have a strong contraction, then we have a lower bound for the basing after reordering so it's choosing a good starting point of the orbit. But of course, not easy to adapt. And of course, we need the extra hypothesis because we have examples of infinitely many sinks. So there's no contradiction immediately, but perhaps it's some extra condition.
Okay, thank you, Gugu.
Okay. Thank you.